Well, now you've learned about section 4.5. You've learned about what the dimension of a vector space is. And there is a rather amazing theorem in section 4.6 dealing with rank. And at the top here, at the top, it says, with the aid of vector space concepts, this section takes a look inside a matrix and reveals several interesting and useful relationships hidden in its rows and columns. Okay, hidden in its rows and columns. So let's look at the first example here, or first concept, a row space. Okay, and we'll look at example 1. So you have seen column space, but what is a row space? Well, they define the row space A here. We have an M by N matrix, and the row space is a subspace of n-dimensional space. Okay, so what they're doing in example 1 is they have this matrix A. It is a 4 rows and 5 columns, and they've written down on the right the 4 rows that make up the row space. Okay, the 4 rows. Now, what they're going to do here is they're going to go ahead. Well, I mean, what does this actually mean? Okay, if we look a little bit below, we're going to get to another example, but the row space of that matrix A is the subspace of 5-dimensional space spanned by rows R1, R2, R3, and R4. Okay, that's what the row space is. Just like the column space is the space defined by the span of the column vectors of a matrix, the row space is the subspace defined by the span of the row vectors of the matrix. And obviously these row vectors, R1, R2, R3, R4 in example 1, have 5 coordinates, so they live all in R5. Okay. Now, an interesting result about the row space is the following. Okay. Let me see. There was one thing I wanted to mention here. Yeah. Example, theorem 3. Theorem 13, actually. So if 2 matrices A and B are row equivalent, then their row spaces are the same. If B is an echelon form, the non-zero rows of the matrix B form a basis for the row space of A, as well as that for B. Okay, so that means that the space spanned by the rows of the matrix A are equivalent to the space spanned by the rows of the matrix B when B is an echelon form. Okay. Now, this is not true for column spaces. When you do row operations, and they mention this here right above. You've actually seen this in an example that we looked at. That if you do row operations on a matrix A, reduce the matrix into, for instance, echelon form matrix B. Okay, that'll tell you what the pivots are, for instance. Well, the column space of the matrix A, the space spanned by the columns of the matrix A, is not equivalent to the space spanned by the columns of the row equivalent matrix B. Okay, the actual span of the column vectors is different, but that's not true for the row space. The row space, the space spanned by the row vectors of a reduced echelon form or of an echelon form matrix B is the same actual space as the original row vectors. Okay, so that's quite an interesting result. Indeed, it is. So if we go here to this example 2, let's see it in practice. Okay, so they want you to find basis for the row space, column space, and null space of the matrix. Okay. So we could put this matrix, this is a rather large matrix, it's 4 rows, 5 columns. We could put this matrix in MATLAB and get the echelon form of the matrix. And if we did that, we would get what you see, what you're going to see now. The matrix A is row equivalent to the matrix B. Now in the matrix B, how many pivot columns are there in that matrix B? How many pivot columns do you see? That's right, Mikhail, 3. And what are those pivot columns? What are those pivot columns? Is it the first, second, and third, the first column and the third column and the fourth, fifth column? What columns are pivot columns in that matrix B? What are the pivot columns? What are the columns that have the pivots? That's right, Belen. That's right, Mikhail. Columns 1, 2, and 4. So this means then that the basis for the column space of A are the 3 vectors that correspond to those pivot columns. Okay, but I want to say this the right way. I don't know if I'm able to highlight this the way I want to. Let me just try. Let me see here. Yeah, I think I can just verbally say this. The first column, I want to say this the right way. No, I'm going to go to the whiteboard and say this the way I want to say it. Example 2. Hold on, where's my thing here? Okay, and it always gives me the big fat marker. Okay, so here we go. Okay. So A is row equivalent to B. And here are column vectors in reduced echelon form. So this is just, I'm taking example 2 and just writing it, portion of it down here. Actually, what I want to do, hold on, let me do better than this. I want to do better than this. Hold on. So the matrix A, just get this blasted thing off. All right, hang on. The matrix A from example 2, section 4.6. It's worth the trouble. Being careful to write everything down right. Okay, so this is matrix A. That's row equivalent to matrix B. Okay, matrix B, hold on, let me get this thing off there. All right, matrix B now. So you could use MATLAB to show this. Here are the columns for matrix B. Absolutely fascinating, really. Okay. So we identify in echelon form matrix B these 3 pivot columns. Okay, those 3 pivot columns. So this means then that a basis for column space A, okay, all right, the basis for the column space A, I'm going to write something down. Okay, I want to just see if I want to write it down, first of all. Yeah. Would this be right for the basis of the column space of A? Column space of A. Hold on, I got some. I don't know what happened here. Is your thing blown? My thing got blown up on me. Hold on. Hold on here. Tell you, you hit one wrong button. Is this correct? Is the basis for the column space of A those 3 vectors? Okay, or hold on. Hold that thought. Or is the basis for the column space of A hold on here. These 3 vectors. Could both answers be right, or is just one answer right? Right, it's the second answer. That's right. Good, David. Good, Mikhail. That's right. The basis for the column space of A, in other words, the when you do row operations on the matrix, the linear dependence relationships between the columns is not preserved I want to say it the right way. Row operations change the, hold on, I'm not saying this the right way. Row operations change the dependence relationships, the row dependence relations. So the basis for the column space of A would not be this, but you'd use the pivot vector, you use the pivot columns in the echelon form of the matrix A to identify then the corresponding columns of in the matrix A that form a basis for the column space of A. And that's this here. So far, so good? Are we okay with that? Okay, good, good. You have to be very careful with that. Very careful with that. All right, good. Now, here's though something that is interesting. The row space of A, the basis, if we want the basis for the row space of A, okay, in that case, if you look at the row space here, okay, think about your pivot columns, but going across. Here's a pivot column. Okay, this is a 0 here, right? Here is another pivot column. And then here is a pivot column. You have 3 pivot columns. Okay? So the basis for the row space of A, the way the book writes it, the way it has it, it writes down 1, 3, -5, 1, and 5. It writes it down this way. It writes down it uses coordinates. 0, 1, -2, 2, -7. And finally, 0, 0, 0, -4, +20. Okay? So with the row space, it works differently. You can use the pivot columns in the echelon form of the matrix B, and the row space is preserved. Now, a second answer for the row space would be this. You could go and look here and choose the rows that correspond to the first 3 rows over here. So a second acceptable answer would be this. Hold on here. Three, 11, -19, 7, and 1. In other words, both of those answers are okay. Both of those answers are okay. The row space for the matrix A here is the same as the row space for the matrix B. Okay? But that's not true for the column space of the matrix A. Column space of the matrix A, you identify the pivot columns by reducing the matrix A into echelon form, and then the columns that correspond, the columns in the matrix A that correspond to those pivot columns in the matrix B, those columns in the matrix A will be your column space. Okay, so that's the difference. Okay, are there any questions on that? They give a proof of why the row space works. In a nutshell, let's say this the right way. I'm looking at the proof of theorem 13 here. If I go back in the book, let me just go back in the book here. Theorem 13. Let me just go back here. I mean, this is what theorem 13 says about this is what we just showed, or what we just said, basically. And, well, you are doing row operations, okay, and row operations are reversible. So it doesn't change the space spanned by the row vectors. That's essentially what their argument is in this proof. Okay, it's not something we need to go into great detail about, but at any rate, that's why it works. Okay, and if we want to, also they mention here about finding the null space. Well, you already know how to find the null space of a matrix. Okay, you already know how to do that, right? That's not a big deal. So now, let me ask you this: how many for this matrix A? It looks like the basis for the null space of the matrix A, there's 2 vectors. How many vectors were there in the basis for the column space of A for this problem? In other words, what's the dimension of the null space of A is 2. What was the dimension of the column space of A for this problem that we were working on? How many vectors are in a basis for the column space of A? Well, if we go up here, it looks like there were 3 vectors in the basis for the column space of A. So you have a matrix that has 4 rows and 5 columns. The dimension of the column space is 3. The dimension of the null space is 2. What's interesting about 3 and 2? We have a 4 by 5 matrix, A, 4 rows, 5 columns. Dimension of the column space is 3. Dimension of the null space is 2. Can we relate 3, 2, and 5? Can we relate 3 and 2 to 5? Well, what if we take 3 plus 2? What do you get? You get 5. No, Mikhail, this was proven earlier. What you had said was something a little different. No. The dimension of the null space plus the dimension of the column space of a matrix equals the number of columns of the matrix. Okay, and that's by what's called the rank theorem. So if we, well, okay, rank, what's that? The rank here is the dimension of the column space of the matrix. Okay, it's the dimension of the column space of a matrix. Okay, hold that thought, hold that thought. So by the rank theorem here, theorem 14, the dimensions of the column space and the row space of a matrix are equal. Okay, that's an interesting result, but it's true. And if you take the rank of A, which is the dimension of the column space of A, and add the dimension of the null space of A, that's going to equal your number of columns. And we can play around with some nice examples in Wednesday's class for that. I think, Mikhail, you had an example. What if the last column's all zeros? I'll make a note of that, okay? And we can play. I mean, we're gonna delve into this a little more on Wednesday. This rank theorem from section 4.6. Okay. All right. So this is just I mean, it's really the key part of section 4.6, but we can. Section 4.6 has some theoretical problems in it that are important too. So we'll continue section 4.6 on Wednesday. One moment. Okay, are there any questions at all before we move on here? Well, before I say goodnight, I should say. Who's feeling good so far? Give me a thumbs up. Okay, good. Wonderful, wonderful. And I'm glad you had a chance to work in your groups. And also wonderful. And I do thank you, everybody, also for being here and participating in the whole class. I think we have just one student who was like logged in but wasn't here, you know. I do thank you for being here. I appreciate it very much. So on that note, I'm going to see everybody on Wednesday, right? I'm going to see you all Wednesday. Good luck if you need to finish version 1 of the exam, and I'll see you Wednesday, Jacob. I'll see you Wednesday. Thank you, and you know, good luck keep working on the MATLAB, and good luck on the exam. Thank you. Bye, David. Bye, everybody. Thank you, Belen. Thank you, Cameron. Appreciate it. Thank you, Dotnell. Okay, Mikhail, no problem. I'll hang out a little bit. Okay, let me take my video off. One moment. One moment. Okay, Mikhail. So I'm here. Oh, I am. Okay. Thank you. All right, I'll stop the recording. Excellent.